Hi everyone, welcome back. Today we will study about hybrid pi model. This is the pretty convenient and effective model to figure out the gain of our BJT amplifier circuit. So let's get to it.
Okay, so in the last lecture, we went through an equivalent circuit called small signal equivalent circuit, or in other words, you can call it AC equivalent circuit. In this lecture, we will discuss another equivalent circuit called hybrid pi. So let's go into it. But before we start, some note on the bipolar AC analysis problem solving. Since we are dealing with an amplified circuit, with superposition applies, we can perform the DC and AC analysis separately. The analysis of BJT amplifier process you can follow with these steps below. So first, you need to analyze only DC source. Okay, so you remove the AC component. You only consider the DC component of the circuit. If you do that, you will obtain the DC solution or the quotient solution or Q point, so which use the DC signal models for the element. The transistor must be biased in forward active region in order to produce a linear amplifier. So remember this. Transistor must be in forward active for it to be linear amplifier. Okay. The second step is to replace the element in the circuit with small signal model or AC model. The small signal hybrid pi model, which we will discuss today, can also be applied to the transistor. And finally, we need to analyze a small signal equivalent circuit, setting the DC source component equal to 0 to produce the response of the circuit to time varying input signal only. So as I say, we're gonna have basically different model, DC and AC, and this is the table of different components for different model. As I mentioned in the separate note for the H parameter, you can always treat the BJT as a two-port parameter. So if I have the BJT as a circuit right here, I can always use a block diagram to represent our BJT. Then I will have the two input port, okay, placing at BE, and the two output port placing at CE. Okay, so first let's consider our input port between the base and the emitter. So previously we got the base current IB, small subscript, okay, equal to IBQ over VT. This VT is basically IB is a constant based on the Q point. VT also a constant based on temperature, okay, multiplied by VBE. So we have VB equal, we can have rewrite it at VB equal VT over IBQ multiplied by IB. If you see in here, because VT and IBQ is a constant, therefore you now have a linear relationship between VBE and IB, and that's what we did before. We tried to establish a linear relationship in our system, right? So if you have a linear relationship, you can extract this parameter out. Okay, you extract this parameter out and you can call it R pi. Okay, and if you remember this slope, last lecture we was trying to figure out this if we basically probe the signal as Q point right here, and instead of analyzing this whole exponential growth, we estimate using small signal, and we figure out the slope for that amplification. So out the 1 over r pi is actually the slope that we were looking for at the Q point. Okay, so just some math. Basically, if you want to prove it, you can do this. If you don't want to do the proof, just accept the result, that's fine. So we have 1 over r pi is the slope. So that means how can you estimate, like calculate the slope? You take partial, which is small amount of IB, and you divide it by small amount of VBE. Okay, so you do that. Then you can plug in all the constant parameter, and finally you can have basically you can calculate the slope as IVQ over VT. So you can accept this how can I say, you can accept this equation as a standard. So 1 over r pi equal IVQ over VT. Okay, so another thing to remember is that this r pi resistance, okay, this r pi resistance is called diffusion resistance or base emitter input resistance. Okay, because we basically calculate this at the input of the 2 port, and this r pi is a function of the Q point parameter. That means if your Q point change, r pi also change. So next we will move to analyze the output port between the collector and the emitter. So previously we have IC is a function of VBE without the early effect, and we will analyze with the early effect later. So we know that delta IC equal to the slope of IC over VBE curve at the Q point multiplied by delta VBE. So you can also rewrite like this. We'll get up the delta. So we have IC equal IS, and this IS is the saturation current. Okay, so it's usually equal 10 to the negative 13 ampere or 0.1 picoamperes, then multiply for exponential of VBE over VT. Okay, so now you can have this slope here. You can represent this slope here with this equation, and finally you can have this to be equal to ICQ over VT. So this slope ICQ over VT, you can call it GM, and this is defined as transconductance. Okay, so now you can write instead of writing this equation to describe the relationship between IC and VBE, because this is a linear equation, so you can represent this whole slope as GM, and GM will be equal to ICQ over VT. Okay, so GM is, if you can see, GM is also a function of Q point parameter. So if Q point change, GM also change. Using the R pi and GM parameter, we can obtain a simplified small signal hybrid pi equivalent circuit. And that circuit is showing on the right here. So you can see, instead of using this block, we can represent the whole 2-port network with this block and plug in R pi and GM parameter to represent our circuit. So let's apply this new model to figure out our voltage gain for the amplifier. So remember this circuit here, this is basically the AC equivalent circuit, our BJT amplifier. So you can replace the BJT portion with the hyperpi model, then you can have this circuit over here, right? So the goal here is we have to derive an equation for the ratio between output voltage and input voltage, which is the gain. So first we have to derive the term for the output. So we have VO field equal VCE over here. Okay, then basically the voltage is you can use Ohm's law. Basically the voltage equal to current multiplied by resistance. To apply a little bit of voltage divider on this resistance right here to get the term for V pi. Okay, and please note that the term VBE can also be represented as V pi in this equivalent model for the phasor notation. So if you use that voltage divider rule, you can get your value for V pi. Also, you just have to flip this term over, flip this one over here, then you can derive the terms for your input voltage. So finally, all you have to do left is to divide the output for the input. Then you can have your equation to express the gain, the voltage gain of the circuit. So let's go through one quick example right here. So given the circuit here, or any of the normal conventional, like any of the BJT circuit that you have, if you have beta equal 100, we will assign that. Let's assume VCC equal 12, VBE equal 0.7, RC equal 6k ohm, RB equal 50k ohm, and VBB equal 1.2 volt. And this is the bias. Okay, now let's try to calculate our small signal voltage gain, which is our amplification factor. So I'm gonna cheat a little bit here. So and we'll assume that we can quickly apply the DC portion of the previous lecture to get to derive that my ICQ. Basically, I need to have the DC solution at Q point. So my ICQ is gonna be 1 milliampere and VCEQ is 6 volt. So then next we need to calculate the AC solution for our HyperPy model. So you remember, if you start using HyperPy model, the first thing you need to tackle is basically just plug in your equation for RPi and GM. Okay, and so for RPi you have from the previous slide, it's going to be beta multiplied by VT over ICQ. So you have ICQ, you have beta, but what is VT? So VT, if nobody say anything, just use 0.026 is the default value for at room temperature. Okay, so when T equals 300 Kelvin, you can use this number. It's the thermal voltage, and do the same thing for GM. You can have GM equals 38.5 milliampere over volt. And finally, you just have to plug in all of your GM and RPi number, and you can have your signal voltage gain to be negative 11.4. So we have assumed that the collector current is independent of the collector emitter voltage in like previous example. However, there's an effect called early effect. It is named after JM Early. It's not because it happened earlier, it's just because it's named after a person whose last name is Early. So the early effect is when the collector current, which is this value here, vary with the collector emitter voltage. So remember, in previous example, we assumed that this current will stay flat when you increase this voltage, but however, with the early effect, you can actually the current will increase. Okay, and basically that value is affected by a parameter called the early voltage VA. Okay, so the generalized equation for the collector current with early effect is basically similar to what we had before, multiplied by a term for the early effect, which is this. Okay. Okay, so now we have a new term here. It's called output resistance. So basically, I have the hyperpie model right here, and the output resistance is the resistance that couple like across, like parallel to the dependent current source and our VE. Okay, so the output resistance can also be defined as the slope of VCE over IC. So this inverse slope right here. Okay, so basically this slope is actually 1 over RO. So we can write down 1 over RO, and I'm going to cheat a little bit. So finally we can write the slope 1 over RO as IC over VA. So finally we have 1 over RO equal to IC over VA. Okay, so we can get the equation for RO to be VA over ICQ. Something to keep in mind, we have a few parameters in here. For example, VA and IS. IS is the saturation current. Okay, usually around 0.1 picoampere at 300 Kelvin temperature. And we have another parameter is VA, which is the early voltage. And this voltage often varies between 50 to 300 volts on silicon-based device. The RO is called small signal transistor output resistance. This resistance can be thought as an equivalent Norton resistance, which means the RO is in parallel with the dependent current source. So now we can have the expanded small signal model for BJT, including the output resistance due to early effect. So on the left hand side right here we have circuit A, which contain the transconductance parameter, and the right hand side we have component like the circuit B, which contain the current gain parameter. So either you use hyperpie model or you want to utilize the beta factor, you can use both in your analysis, but you always need to consider that this RO or output resistance is contributed from the early effect that we mentioned earlier. So that's the end of today. There's a few things I want you to do. First is I put on a practice problem regarding early effect in Canvas module. So please review it. If you have time, please work on, and if you can work on example 6.2, that would be fantastic. Finally, I have some reading assignment for you. Please read the input and output resistance section and the equivalent circuit for PNP transistor section. It's in the textbook between page 386 to 388. Okay, so I might not have time to cover those two sections, but it's pretty short. I think you can like read through it quickly, and it's pretty similar to NPN. Okay, thank you.
It for today, and I'll see you guys next time. Bye bye.